All right. So the question is, given the drawing right here, why would we use such a facade? Is the first part of the question. And the second part is we want you to locate the high air pressure. We want you to locate the position of the low air pressure and identify the place on the image with the highest air temperature. So I'm doing a renovation on my house, and as part of it, well, this is not part of the renovation, but it kind of is. This is let's say the old house I moved from had this really cool, what was it, 1.5 inch, which is like the narrowest width you can get, I think, um, maple flooring, and we just love that maple flooring. So we put it in the bathroom in the powder room of the new house, and it kind of wraps around, and then it wraps around the ceiling, and then wraps around this wall, and then there's a reveal here, and then this wall, as you can see, is tiled, and it's really hard to take a photo in a bathroom, especially a powder room as small as this one. But this is the other side of that. So this is the brick fireplace that we exposed. This is more of that maple flat panel radiator, a little position for the toilet paper, which looks like it's running low. I just took this photo, so I got to fill it up again. But then on the top, I really hate all the bathroom fan plastic covers. They all look nasty. So we just made a really simple kind of metal cover to cover the bathroom fan. And on the outside, when it's not on, when the bathroom fan is not on, so there's not really any meaningful pressure on either side of this is what it looks like. Now, when it is on, because I took this picture when it wasn't on, and I took this picture when it was on. And if you see there's no difference, that's the problem, because they just a few days ago replaced this, both of them actually. And there's like a magnet here. And so the way it works is here's the house, here's the duct going to the powder room in section. And then there's like a damper. And in this case, the damper is on a hinge, and the hinge has a little magnet there, and it continues down. And when there's airflow pushing it, then what's supposed to happen is it's supposed to kind of fly open a little bit from the pressure, the positive pressure on the windward side, on the upstream side of the damper, relative to the negative pressure on the downstream side. Now it's, out here where I'm calling it negative pressure, it's not really negative pressure. It's just atmospheric pressure. And this is one of the problems that I don't really think NCARB understands when they ask you these pressure questions, is that everything's really relative to something, and they don't seem to give a reference value. But these pressure questions they ask, I know what they're trying to do, and it's important what they're trying to do, but they're really oversimplifying it to the point where it almost doesn't make sense. But anyhow, we have the positive pressure here, the negative pressure there, and this should be flying open. And the only reason I didn't even know to check is because, well, I'd love to take credit for it, but I didn't even notice it. I'm the acoustician HVAC guy, and I did not notice that the fan had gotten louder in there, but it gotten way louder. And my wife was like, man, the fan just got louder a few days ago. And I'm like, huh, that's around the time that Eric swapped out that guy. And so even then I didn't put it together. And I mentioned it to Eric, thinking maybe there's some obstruction. And then he turned it on and went outside and said, oh, it doesn't open. Because like I said, there's two magnets here. And so we're going to try it with one, I think, and try to figure it out. But anyhow, this is all relevant because that's one of the questions we're asking. So the first question is, why would we use such a facade? And the facade is called a double skin facade. And the main reason, as far as NCARB is concerned, that we use the facade is because the idea is there's glass here, and then but there's air that's allowed to go through a damper here. So if it's cold outside, say it's 10 degrees outside, it's still going to be about 10 degrees in that cavity. And then in here, there's double glass. That's kind of the skin of the building. This particular building may have some thermal bridging issues, the way I drew it. And so the idea is that when the sun comes in, it heats up that space in between, just like a greenhouse. And some of that heat, that greenhouse, the reason the greenhouse gets hot is it's using up some of the sun's heat. And so the theory is that the this heat is heat that would otherwise have gone in the building, and we're reducing the cooling load on the building in the summer. But frankly, big buildings, and most of the buildings that have double skin facades are actually quite big. These big buildings, you guys know this if you take an Amber book, and NCARB doesn't seem to know this, but big buildings use almost no heat even in the cold parts of winter because they generate so much internal heat from people and equipment and lighting. But these days our lights are much less heat producing. So much less. It's actually one of the places we've done the best in terms of fighting climate change. Is our lighting is just way more efficient than anyone could have predicted 15 years ago. But anyhow, as this, we of course don't want this greenhouse in between this area in between to get hotter and hotter. We want to ventilate it. So we have another damper at the top. And so by natural convection, or more realistically by a fan, but in theory by natural convection, architects love the idea of natural convection and not using a fan. The air is going to move up in that space as it heats up, and it's going to go out the damper. Now, the reasons we typically use a fan are, well, we can't always trust that the sun's going to be out and it's going to be hot enough to really, have enough pressure to really push that damper open, as we saw with my bathroom fan. But also because sometimes the wind is blowing this way, and then that blows the damper shut. And so we need some way to kind of, and even if it doesn't blow the damper shut, let's say there was just a grill there or something like that, it still would blow the air. It would blow the air. It would blow the air back. Let me go to a different color. It would blow the air back down the wrong way. So a fan means that even if the wind's blowing the wrong way, or if something's kind of wacky, the air will still be moving up and will be exhausting this greenhouse and keeping out the heat from the sun that would have otherwise gone in. Now, in reality, it doesn't really work, but NCARB does not know that. And most people don't know that. They're pretty rare in the US. They're less rare in Europe, but they're still rare in Europe. And so that's what we're looking at when we're trying to do this. Is ostensibly that's what we're doing. I'll talk a little bit what we're really doing, but that's ostensibly what we're doing. Now, why doesn't it work? I don't know. Nobody, I've talked to experts. They don't really know. In theory, it should work. And I don't want to say uniformly experts say it doesn't work, but the 2 or 3 papers I've read and people I've talked to who have done research in this area say that their experiments show that it does not work. And they also suggest that other people's experience shows it does not work. And again, I'm not really quite sure why. Anyhow, so let's locate the high and low pressure. So we're going to have, because the air is moving in, we're going to have we'll have a low pressure here because it's atmospheric pressure, but just in the same way as my bathroom fan damper. On the outside, it's lower than on the inside because on the inside it's going up. So that's why it's kind of weird to call it low pressure, because it's just atmospheric pressure, but it's low relative to the high pressure on the windward side or the upstream side of the damper, as that air moves up and pushes against the damper. So the high pressure would be here, or really probably anywhere up here, and the low pressure is here. And then likewise, we have a low pressure here, or here, or both places, relative to the high pressure here, because the air is being drawn in by this low pressure, and it's going through. And on the back side of that damper, it's relatively low pressure, and so it's high pressure out here and low pressure in here, and then it builds up again on the other side of the damper, and it kind of makes sense, right? Just intuitively. Now, if we go to our fourth question. Where is the place on the image with the highest air temperature? The place on the image with the highest air temperature is going to be generally up in here, because that's where the greenhouse that's building up in here, the hottest air is going to move to the top. So that should be the place with the highest air temperature. based on the really simplistic diagram. Now, of course, who knows what's happening in reality at any given moment. But in general, that's, I think, a pretty safe answer, is kind of the best answer. I'm not going to go too far into this. This was actually the subject of a more broad discussion of double skin facades. Was the topic of a 40 minutes of competence almost exactly 2 years ago. And it's in a flash. For those of you guys who have access to the Amber book, it's in the flashcards. There's a link to it in the flashcards if you want to see more of this. But the idea is this: that that we can have a second skin on the outside, and we can bring air. Now we're going to bring air either from the very bottom and bring it to the very top, or we're going to kind of do it floor by floor. And what that allows us to do is it allows us to open the windows on each floor without having to worry about either on the fourth floor, maybe not a big deal, but some of these buildings are 60, 70 stories. And on the 40th or 50th story, we usually can't open a window because all the wind would blow all the papers off the desks. So this allows us to open the windows and get some true fresh air without having to worry about that. And also, we don't have to worry as much about maybe it's bringing your kid to work that day, and maybe you have a 3-year-old who grabs a stapler and wants to chuck it out the crack in the window that's formed. And so in this sense, it won't fall 60 floors and kill someone. So there's just kind of a safety factor, or a safety issue that gets resolved by this. And actually, that's probably one expert I spoke to who's done some research in this area. He feels that this is the real benefit. The thermal benefit really isn't there, but this is the real benefit, is that and I'll go through 4 other benefits, but this is the real benefit he feels, is that you can open the windows. So you can have an apartment or an office high in the sky, and you can open the windows and things still work. And so, this is the idea that it kind of builds up. This is one of the earliest, maybe the earliest. It's in the UK version of this. Now, what's this distance? It depends. And I don't know what it is in this particular building, but generally they vary from somewhere around 8 inches on the narrow side between the outside pane and the inside pane, to something like 6 feet. They can be as big as something like 6 feet. This is a project in Germany. This is, of course, Norman. A disproportionate number of these double skin facades are Norman Foster buildings. This is, of course, Norman Foster's Gherkin building in London, and it has a double skin facade. Although they don't. There was an incident like in 2005 where a window fell. I don't know if it fell within the double skin or outside the double skin. So they really don't let people open them much anymore, if at all. And in fact, some of the tenants have in their leases, in their agreement, that they're not to be opened. They don't want the mixed mode mechanical ventilation. Mixed mode meaning open a window and or bring in outside air mechanically. They want just traditional bring in outside air mechanically as needed to keep fresh air in the building. Those of you guys who have taken the Amber book, HVAC, know what I'm talking about. Many of the rest of you do too. So they don't really do it that much anymore, but this was kind of the idea behind it, that there would be these angled, streams of air that would go between. And this is the Commerzbank building, also by Norman Foster. This one's in Germany. And in this case, it goes in at each floor and then out at each floor. These cut lines are kind of close together, but it goes in at one floor and then up, and then it can go out at the floor above, or at the floor above. And you see in between the shading, and we're going to talk about that too, because the shading is one of the other advantages to this, because normally in a big building like this, especially a glass building like this, by far the biggest energy user in terms of peak energy, and often in terms of annual energy, is the air conditioning and working to cool the building when the sun is out. And again, it's just like your sun's out in your car. How hot does your car get when the sun's out? Even on a not that hot day, it may only be a 75-degree day, but if it's sunny and your car is facing the sun, it could easily be, 110 degrees inside your car. And so that's huge. It's a huge amount of BTUs per hour that are coming into your car. Well, that's coming into your building too, if your building is all glass and it's heating up your building. And so we would like to shade the building. Now we have a few options. We can put exterior shades, and those can be really beautiful, but they require a ridiculous amount of maintenance, and they often break. And because they're outside, they're often thin members that are outside, so they warp. And those you guys maybe can find some stuff online, or maybe if you live someplace, they're beginning, and I'm going to say 2007, and kind of maybe peaking in 2017, I'll say. But it's still around a lot. Is these kind of buildings that have these wood screens with these thin horizontal wood slats. And they're really beautiful. They're amazing wood screens, but every photo I've ever seen of these are always like right when they open, right when the building's completed. With one exception, I've seen the Herzog and de Meuron building with one of these over that's 20, 30 years old, and they sag. They're really thin wood that's horizontal in wet climates often. So they they warp and they twist and they split and they rot and they sag. And so if any of you guys live near a building that has once beautiful horizontal wood screens, send them to me, 10, 15 years later. I'm kind of curious to see if they hold up. But anyhow, these require, outside requires a lot of maintenance and often starts to look bad almost right away. Inside is only about 80% as effective. So if you have shades inside the building, it's only about 80% effective. Why? Go ahead and put in the chat. Why would inside shades be not as effective as outside shades? Now, 80% is not bad. Someone asked if I'm going to post the other video on the Amber Book website, the one from before that I did 2 years ago. It's been on the Amber Book website. It's been on the Amber Book, within the Amber Book course in the flashcards for years. So it's in I think PPD flashcards. The heat's already entered the space and it's trapped between the blinds and the window. You guys got it. It's pretty intuitive. So it's not, 80% is not bad, but not as good as outside. So this kind of is a good compromise because we can put the shades in the middle here, and then we can control them from inside, from a switch inside, and we can raise or lower the shades so we can provide our shading and still have control of it. Because once you start putting motorized things outside, then they really go bad. I mean, the Institut, the Institut of the Arab World, the Institut Arab Mondial in Paris is a great example by Nouvelle. You guys know that building. If you don't look it up, you definitely know it when you see it. These buildings that have kind of movable elements on the outside or even on the inside, they always break, and there's never anyone to fix them. I used to love that stuff when I was in school, and now I kind of hate it because I've seen so many examples of they're just stuck in that particular setting. But anyhow, we protect the shades here and the motors and all that stuff from dust and from warping and from getting all cattywampus. And then, but they're still on the outside of the actual proper building enclosure, which is here with the double window. This is not the double skin here. This is just IGUs, insulated glazing units, double pane glass, what you call double pane glass. And then here is the exterior skin. And then this is the space between it. So you can, a maintenance person can walk along here. I don't think regular people can. And it's great. So it allows for the air to move up between the inside skin and the outside skin in the interstitial space. And then you have these things that kind of pop open. Not sure if they do automatically or manually. I don't think this is that building. But sometimes they come in cartridges like this where because it's really hard to, without having a bunch of thermal bridging and all kinds of leak issues and so forth, it's really hard to suspend one piece of glass off of another, off the building. Glass is really heavy. So these are just different things. So here again, we have the cavity inlet, the cavity outlet, we have the shade. So so yes, it may or may not work for cooling, but that's your answer for NCARB. But just so you know, it has these other advantages that probably work. One is you can open the window. One is you can shade better and in a less maintenance intensive way. One is you can reduce pollution in cities. If a truck, bellows smoke, you can either filter that out or just hope that the outside glass kind of acts as a buffer. One is it reduces noise, depending on what the openings are in this cavity outlet. It will reduce noise somewhat. So if an ambulance is going by or something like that, it would probably be a little less and maybe a lot less, depending on the configuration of the cavities. Noise inside, although not as much as you would think typically. And it does, those big buildings I mentioned, they don't need a lot of heating, but when they do need heating, when it's cold enough, as it is often in Europe, and especially on the perimeter, because this stuff is on the perimeter, it's not unusual for buildings to need some heat on the perimeter. And there is some evidence that in a heating mode, this is a benefit. But if you were asked, you would want to definitely say it's used for cooling mode in summertime and warm climates. All right. I thought
Hey, Michael,
I would spare you. Yes.
Before we pivot, there have been a couple of questions in the chat that I think would be good for you to address.
Sure.
One is from Maggie in the Q&A. Is there a convective loop in the double skin facade?
Oh, that's a great
in the
question.
Course that anything greater than 4 inches will create a convective loop.
That's maybe I remember I said no one knows why it doesn't work. Maybe that's why it doesn't work. Maybe what's happening, that's super interesting. This is from Maggie, you said? Maggie, I think you're ready to take the test. If you haven't yet scheduled it, please schedule it soon. That is a really, 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 really good question. So in a convective loop, you have a hot side and a cold side. So let's say it's wintertime. Well, I guess we'll say it's summertime. And so you have the warmest air is on the outside. So that air is moving up. And the relatively cooler air in the summer is on the inside. And the inside pane air is moving down. So what would otherwise be going up, again, if it's drawn up by a fan, maybe we don't worry so much about the convective loop. But if we're relying on a passive system where there's no fan, I could totally imagine there becoming a convective loop when you have spaces that are bigger than, and actually if you have tall spaces, it can be you get convective loops much more readily in tall spaces. Because there's so much separation, the heat, it goes to the top. There's so much more room for it to go up. And these are generally really tall spaces. So maybe that's why it doesn't. I'm glad you interrupted me for that one, Tom. That's definitely worth interrupting. That was a great question. What's the other one?
The other one was from John in the chat. He's asking about fire protection and if this creates a channel for fire to move from floor to floor.
I've often wondered that also. I mean, it's generally, of course, not conductive. Not flammable, this stuff. And that is an issue, certainly. I mean, I'm not sure if it's really considered part of the building or if it's just basically outside the building at that point. That's a good question. I assume that is an issue. And for those of you guys who don't know, I'm sure most of you know, but if you haven't looked up if you don't remember what happened in, I don't know, I'm going to say it was 2017. It's called the Grenfell, I think Grenfield, and maybe Tommy or someone you can put a link to it. But it was a fire, to the YouTube video about it or something for you guys to look at later. But it was a fire in London, the Grenfell Tower, where there was insulation, but flammable insulation, put on the outside of the building to make it better from an energy use point of view. That kind of thing is not allowed in the U.S. and experts were testifying for years that it should not be allowed in Great Britain, but it was. And there was a stove fire on like the 4th floor or something, and the flame went out the window and caught the exterior insulation that was outside the building. And the whole building went up very quickly, and a ridiculous number of people died who should not have died. So you guys can look up that one later, but that's just 2 really good questions. I think if whoever asked that one is probably also ready to take the exam. That's a very good question. So we have time for 3 questions if you have any. So raise your hand if you have a question. We'll give you 20 seconds to come up with one. All right, Natalie.
Thank you for the presentation. Could you clarify, when I first saw the question for the class, I was like, oh, people use a double skin facade to create a convective loop so that it cools down the skin envelope of the building. Mm-hmm. But then it kind of threw me off when somebody asked about the convective loop being why it doesn't work.
Yeah, so it creates a convection, but not a loop. So a convective loop means it goes up one side and down the other, but we want it to go up and out, not up one side and down the other.
Okay, so if it goes,
it's the word convection loop that makes you. It's the word
Yeah.
convection just means that the convection means heat transfer through a fluid medium. And in this case, the fluid medium is air. So let's just call convection heat transfer through air. So that happens in lots of different ways. If you open your window and it's cold outside, it's going to get cold inside. That's convection. Likewise, if a football player takes off his helmet and there's steam kind of rising upward from his head, that's natural convection. That's warm air moving upward. That's a different type of natural convection. If there's air moving down the duct, it's bringing heat from the air handling unit to your space. That's also convection, although not natural convection. And a convective loop is what happens if you have two pieces of glazing, and this is definitely in play on the exam. You have, I shouldn't have done blue. I'm going to pick a different color. You have two pieces of glazing, and it's 10 degrees outside, and it's 70 degrees inside. And what's going to happen is the outside is going to be the outside piece of glass is going to be, or it doesn't have to be glass, actually. It can just be a wall cavity. The outside is going to be quite cold, so the air is going to drop. And on the inside, the air is going to rise because it's warmer. And so you have a loop. And the reason that we care about convective loops is they can actually speed the transfer of heat, in this case from inside to outside. So it can make your building colder than it would have been even if you didn't have a loop. And so it's because it's like a breeze. Now it's not a breeze so much that you could stick your hand in the wall cavity and your scarf would be, stick your head in the wall cavity and your scarf would be blowing straight upward, as like if you were in a convertible or something. It's not like that much wind. But there's just kind of a steady breeze. If you've ever seen toilet paper over a radiator in an old building, you can see the toilet paper kind of waving back and forth as the heat rises from the radiator. And it's the same principle, of course, it's just convection. So convective loop, from a thermal point of view, is a bad thing. And it goes up one side of a cavity, typically a wall cavity, and back down the other. And it doesn't happen in a ceiling or roof cavity because, well, it sometimes does, but not really, because there's not that up. There's not an up and down kind of thing. I mean, it's colder. There's gradients that form where it's colder on the top in the winter and warmer on the bottom if it's cold outside. And but it's not the same.
It doesn't cool your building down, though.
It does cool. In this case, it does cool your building down, but it's winter time in my example, and we don't want to cool our building down.
Understood. Okay. And then when it's the summertime and it's really hot, it doesn't cool your building down?
No, because it brings the heat in. So in the summertime, it's now 90 degrees outside. And so it just flips it around the other way. But the thing is, the delta T, the difference between 70 and 90 really isn't that great. So in other words, because in the summertime, the temperature outside is not that much warmer than inside, even on a hot day. But on the wintertime, it's a huge difference. It's usually not a summertime phenomenon we're that worried about. But yeah, in the summertime, it brings this air up. And it brings this air down, cold air down on the inside. And so the 90-degree air is being moved to the inside by basically a handoff or a handshake between the air within the cavity. And if that cavity is greater than 4 inches, it's likely to happen. Now, that's a rule of thumb. It will, if it's a very tall cavity, it will happen even at lower, and it will happen.
So you don't want to create a convective loop ever.
Nope, never.
Got it. Okay. And the double skin facade was just kind of like it happened, and then they stopped doing it.
No, they still do it. They still do it, but it's not a loop. They're trying to cool their building. They're not trying to. So what this is doing, what I just drew is doing is it's moving heat from inside to outside or from outside to inside, depending on the season. But we don't want to move heat from outside to inside. Completely separately, what the double skin facade is doing is saying there's heat that would have otherwise gone in theory, and we can exhaust it. We can kind of capture it before it goes inside the building and send it out. So that's convection, but not a convective loop. And since we
Thank
don't
you so
have
much.
oh, you're welcome, Natalie. And since we don't have any other questions, I'll go ahead and say good night and get licensed. Bye, everybody.
Okay. Thank you.